In this optimization problem, we're going to construct a box whose length is 3 times the base width. The material used to build the top and bottom costs 10 feet, $10 per square foot. The material used to build the sides costs $6 per square foot. If the box must have a volume of 50 cubic feet, determine the dimensions that will minimize the cost to build the box. So again, we want to minimize the cost. So this is going to be our real equation that we work with. Okay, and let me write that one right away. So cost, well, if we think about the bottom, we've got 3W by W. Okay, if you look at that, you know, I in the picture I drew, I already changed it from just length and width because I knew the length was 3W. So the base and the height are 3W times W, so it's 3W squared, and I have 2 of them. Okay, I'm going to write 2 times 3W squared, okay, because there's the top and the bottom. And it told me that cost me $10 per square foot, so I'm going to put $10 multiplied by that area. The sides are $6 per square foot. Well, I've got 2 sides that are H by W. Okay, and I've got 2 sides that are 3W by H. And again, this whole thing is being multiplied by 6 because it's $6 per square foot. So you know, you can immediately do some cleanup here. 10 times 2 is 20, times 3 is 60. So we've got 60W squared plus 12HW plus 6 times 2 times 3 is 36HW. And we could combine our like terms and have 60W squared plus 48HW. So already we've done a lot, but we do have 2 variables, so we have to go to our constraint equation. So let me put that constraint equation right over here under the picture. Okay, the constraint equation in this case has to do with the volume, and they tell me that the volume has to be 50. Well, volume, of course, is length times width times height, so 3W times W times H has to be 50. So 3W squared H is 50. Now, looking over at my equation, you know, I have only one H, so maybe I'd like to get rid of that. That would probably be the easiest. So I'm going to say that H is equal to 50 over 3W squared, like that. So now we take our constraint part and we go back and put it in cost. And again, do not do too much with that constraint equation. We care about costs. It's what we're trying to minimize. So let me bring that over here and do some substituting. Okay, so cost, still 60W squared plus 48. Now I'm going to replace the H with a 50 over 3W squared multiplied by W. I can do some more cleaning here. 60W squared plus, well, 48 divided by 3 is 16. 16 multiplied by 50 is 800. And you'll also notice back up here we had a W and a W squared, so it's going to be over W. Now, knowing that I'm going to do the derivative, I'm going to rewrite this as 60W squared plus 800W to the negative first. Now let's do C prime, or if you want to think about it like I do, Leibniz dC dW equals 120W minus 800 w to the negative second. Let's put it back to not have a negative exponent. That. And we want this equal to 0. So let me solve this. 120 w minus 800 over w squared equals 0. Wouldn't be a bad move to maybe just move this over to the other side and have 120 w equals 800 over w squared. Maybe just cross multiply. So we have 800 equals 120 w cubed. Divide by 120. 800 over 120 reduces to 20/3. And of course now to get w we can just cube root 20/3. And we could put this on a number line, the cube root of 20/3. We could plug in a number less than that into our derivative. We're going to get a negative. If we plugged in a number bigger than that, we would get a positive, meaning this is indeed going to give us a minimum amount of cost. Since the original function asked for both dimensions, now that we had w, we could certainly go back and get the length because it was just 3w. We could also get the height. I'm going to stop here just in the interest of time, but that's how we would at least begin to solve this and at least get what w is.